Now we're going to use the definition of the dot product to prove one of the fundamental results in doing higher mathematics. It's the Cauchy Schwarz inequality. Okay, first remember that if we have two vectors, let's say u and v, okay, and we're gonna assume that u and v are in Rn. Okay, so we're gonna prove this inequality for Rn. That means we have vectors that have n components. Okay, in our case here, we know that in this case, if we denote the component or the coordinates of u by x1, x2, xn, and the component of v as y1, y2, yn. Okay, we have seen that the norm of u can be written as the sum of the xi squared. I is going from 1 to n. Okay, and the square root of that. The same thing for v. Okay, here we have squared and the square root. This is the norm. Okay, we have given examples when we are working in R2. Okay, so if we have some vector, let's say u in this case has components x1 and x2, in this case the norm or the length of u is just x1 squared plus x2 squared. This is the same thing here. Okay, and now we want to use the dot product to prove our result, which is the Cauchy Schwarz inequality. Remember that we defined the dot product in this manner. First, u dotted with v is the norm of u times the norm of v times the cosine of theta, where theta is the angle between u and v. Okay, we also defined this one as the product, the sum of the product, the component-wise product, and the sum. Here, if we have x1, xn dot with y1, yn. So we have this one here as x1 times y1, x2 times y2, and we add all of them. So we multiply and we add component-wise. So we have x1, y1 plus x2, y2, etc. until xn, yn. We can write this sum in this sigma notation. Okay. Here, when this is in R, just a number. Okay. Here, when we take the norm, okay, if we square both sides, or we take the norm here, okay, because this is just R, it belongs to R. This is a number. So here, u dot with v squared, it's gonna be the norm of u squared times the norm of v squared times the cosine of theta squared. But here we know that the cosine of theta is always less than 1. That means cosine squared is less than 1. So this gives us that this one here, u dotted with v squared, okay, is less than the norm of u squared times the norm of v squared. Okay. Now, if we take the square root, we take the absolute value of u dotted with v. It's going to be less than the norm of u times the norm of v. Okay. And if we write this one in the component by components, we have this is just this sum here. So here we have the absolute value of x sub I, y sub I in absolute value between 1 and n is less than the norm of u is just xi squared, I between 1 and n, and square root times y or I between 1 and n, and the square root here. Okay, so this is the Cauchy Schwarz inequality, and this is how we prove it. Okay, so it's just writing everything and following the logic to get to this statement. Okay, so this is we proved this result for the case where we have vectors, okay, that have n components. That means we are working in Rn. Okay, we can prove it in other sets or other spaces, but this is, if we know this one, we can do it for any other space. Okay, thank you.